And let's look briefly more at the transistor nodes. Okay, so those of you whose circuit is not behaving correctly, let's look at the circuit diagram. Okay, so the lights are completely separate from this. Okay, so you got your lights, but they don't directly interface with this part of the circuit, with the exception of the output light. Okay, so what are pin 2 on basically all of these transistors? Pin 2 is the one in the middle. What should that connect to? Both. The two inputs, so one to one, one to the other. Okay, make sure that with your two ends, one is connected to one input, the other to the other, and same thing with the P. Okay, that's an easy mistake to make. All right, in this case, pin 1 of the P's is connected, both of them are connected directly to 5 volts. Yes? Okay. And both of the pin 3's of the P's are connected to the output zone. Then for the ends is where it's a little different, right? One of the pin 1's is connected to ground. The other pin 1 is connected to the first guy's pin 3, and then the pin 3 of the other is connected to the output, okay? So in terms of our Christmas lights, what do we have here? The P's, I'm sorry guys, you can't see the screen because a certain stupid professor, let's try this again, shall we? You mean y'all aren't psychic? No? Okay, that's better. Yes? Okay, so like I said, pin 2's are connected to the inputs for all of them, okay? And just one to one and one to the other for each pair. So in our Christmas light analogy, right, how are the two P's, those are the guys at the top, how are those wired relative to the power, the 5 volts in the output? They're wired in parallel, right? Okay, so parallel means that can power get through one of the transistors sort of irrelevant, or where we can ignore what the other one is doing? Yes, okay. So that means they're in parallel. In terms of the Christmas lights, this would mean if you've got a string of Christmas lights that's wired in parallel, if one of them goes out, no problem, right? That one's out, okay, no big deal. Yeah. Mm, nothing. They're not on that diagram. Yeah. So this is the diagram of just the transistor part of it. Okay. So the LEDs, if we were to draw those, would be kind of over here, sort of separate. They'd still be connected to the inputs and also to ground, but they're not directly part of this. Okay. And yeah, I know that's maybe a little confusing now. That'll be better later. Because, like, if we think about building like a microprocessor or chip, right, it's going to, excuse me, have thousands of these kind of things, but there's no LEDs, right? So we're only putting the LEDs on the circuit so that we can see visually what it's doing and make sure that it's doing what we think it's doing. Okay. Yeah. Okay. So the two P's at the top are in parallel. Yes. We're good? Okay, and the two ends at the bottom are in series. Yes? Okay, so that's the sort of overall wiring structure. And one of the two things I want to do today is sort of explain why it is that I know that one is going to be in parallel, whereas the other will be in series, okay? And then also, well, if the top is in parallel and the bottom is in series, could we make a new circuit where that's flipped, where the top is in series and the bottom's in parallel? Sure, right? Well, what does that circuit do? Well, we'll find out, okay? All right, so the sort of objective here makes sense. Okay, so let me go back to the iPad for a moment, because what we need to talk is basically a little bit of what's called Boolean logic. Okay, so let me sketch just the in part of the circuit. Okay, so we have output. Oh, let me put it back to here. We have our output, and then we have our two transistors, and these are 2N7000s. Like so. Okay, so this is only half of the circuit, yes? Okay, so what I want to know is when is the output what I'm going to call pulled low, okay? Meaning that there is a connection between the output and the ground, which is this symbol, by the way, you guys have picked up is the symbol for ground, okay? So being pulled low means that the output is at 0-volt potential, okay? Okay, so under what circumstances is there a connection directly from the output to the ground? So output is connected to ground if what? So this will be in terms of A and B. Both are off or both are on? Both on. Okay. Okay, because remember, an N-type transistor, if you apply voltage to the gate, which is the pin 2, it allows current to flow between the pin 1 and pin 3. So putting voltage on the gate turns it on. Okay, and so there's only a connection between the output and ground if both of these things are on. Okay, okay, so what that means is that the output here is of this form. Okay, it's the output is not A and B. Okay, now why the not? If A and B are both true, on, okay, what happens to the output? It is connected then directly to ground, which means the output is 0 volts. And what do we think of 0 volts as being? Off or logical 0. Okay, is that okay? Right. So that's why there's the not there, because if A and B are both on, the output is actually off, not on. So it's backwards of what you might have initially guessed. Okay, is that okay? Yeah? You sure? Okay. All right. What's another way that I can write not parentheses A and B? Let's just think in English for a moment, okay? If I ask you the question, are you in math class and a computer science class this semester? For some of you, that's true, and for some of you, it's not. Okay, fine. Well, what would be the opposite? So how would you know it was true that you were in both computer science and math? Like, under what circumstance would that be true? You're in both, right? I mean, it's almost silly the way you say it, right? Okay, so when is that statement false? Well, when you're not in both, yes? But what's another way to say that? Huh? You are not in math or you are not in computer science. Okay, but it's not nor because you could still be in one of them, right? Now, it's true, if you are neither in math nor in computer science, then that's still true, okay? But the only, like at minimum, you are either not in math or you're not in computer science. Possibly you're not in both, right? But you guys see that the or already captures that possibility, right? Because when we say or in computer science or electronics or whatever, what do we mean? Which kind of or? The inclusive or, which means that both is a valid possibility. Okay, not the getting dessert from your mama. Okay, or okay, which is exclusive. Yes. Okay. So what you guys just teased out in English is the following equivalent or the following statement. Okay, so you guys just teased this out that not of an and becomes the or of the nots. Has anybody seen that before? Maybe written slightly differently, but no? Okay. Hmm? You've seen it before? Yes, keep talking. Yeah, okay. And you may write it slightly different because there's different notations in logic and electronics and whatnot. So, for example, you might have seen it written this way. These are both the same thing, not oops, sorry. Um, A and B is equivalent to not A or not B. Okay, so that's how you would tend to write it in a symbolic logic standpoint. The little hook thing means not. Upside down V means and. Right side up V means or. Just a different way of writing it. Okay, so what we've discovered there is one of two laws of logic called De Morgan's laws. Okay, and basically it in a almost an algebraic sense, what it says is how does a not distribute over parentheses? Okay, so I'm going to think about this in sort of algebraic terms when I say things like distribute, right? Because what does that mean in like regular algebra? If you had A times B plus C in parentheses, what is that? What's another way of writing it? You could distribute the A and you get AB plus AC, right? So that is a distribution law in algebra, or really the algebra that you guys learn in like middle school, right? Boolean algebra or logic is another type of algebra, but you can think of it that there's some similarities structurally between them, okay? Because that's just what we were doing. We were distributing one operation over another. Yeah? Well, that's great. Did you guys know that there's more than one algebra out there in the world until this morning? Yeah. Yeah, there's lots of different algebras. And there's some of them that are really bizarre. Um, so I'll give you an example just to kind of whet your appetite for if you want to, study more math. Um, in algebra, is A times B the same as B times A? could you conceive of an algebra where in A times B is not equal to B times A? Okay, that's a personal problem there, Teo. Yeah, you prefer not to, okay? So it's actually true. There are algebra structures where in that operation, doing it the other direction actually changes the answer. Now, in a very common one that we use in mathematics, reversing the order actually throws a negative out front. So AB equals negative BA. And I'll give you a good example of a type of multiplication where this makes sense. How many of you guys have ever heard of the cross product? How many have taken physics? Not yet. Okay, well, I'll give you a good example of this. So there's the door handle, right? Okay, if I turn, or like imagine I've got a screwdriver. If I turn the door handle or the screwdriver, which way is it going to turn the screw? Well, it depends on which way I turn the handle, okay? So if I turn the handle one way, then the torque vector points in one direction, and if I flip the way I turn it, the torque vector goes in the other direction. And the way you compute this is what's called the cross product. So if I have two vectors, vector 1 and vector 2, okay, the cross product of them is perpendicular to both of them. Okay, that's just how it works out. But how do I know which direction it points? What's the trick? You all have one of these. You have a right hand, okay? So what I'm going to do is orient my right hand along the first vector and curl my fingers towards the second vector. Which direction is my thumb pointing? Up. That means that that's the direction of the cross product. And if I flip the order of the vectors, then I'd have to put my hand here and curl that way, in which case my thumb is pointing down. So, and negating a vector just makes it point the opposite direction. Yeah? Okay, how many? Yeah. Okay, anyway, back to Boolean algebra, right? So what we have just discovered here is one of the two fundamental rules of Boolean algebra, okay? Namely, and I'll write this down. This is the first, and there's a second one that looks very similar, of what are called De Morgan's laws, named after Augustus De Morgan, mathematician from the 19th century. Okay, so what I want to do though is then, have I drawn the entire circuit contraption here? No, I've only drawn the in part of it, but I haven't drawn the P part of it. All right, but I claim I'm ready to draw the P part of it because it's this form here. Okay, well, let's think for a minute. Or means parallel, and means series. And what type of transistors did we flip to on the P side? Well, the P ones, right? Okay, so a P-type transistor, when is the P-type transistor on? Yeah, when the input is off, right? Which means that the P-type transistor does opposite of its input. Not A, that's the first P, not B is the second P, and how are they wired? In parallel, right? Well, there we go. So when you're designing one of these circuits, basically if you figure out what it wants to be, figure out the in part, use De Morgan's laws, and that tells you how to do the P part. Okay, but it's essentially this. If the in part is in series, the P part is in parallel, and vice versa. And the in part uses ins, and the P part uses P's. Okay, so this is the complementary aspect of CMOS, right? Is doing it in these sort of opposite pair-like structures. And now it's like, oh, that makes so much sense, right? Maybe it'll sink in. Okay. All right. Let me write the other De Morgan's law because we're going to need that in a moment. Okay. So these two collectively are called De Morgan's laws. Okay. So there's just two of them, but I've written them in um, both, well, two different ways of writing each one. Okay. So, how many of you guys are going to want to do a CS minor potentially or even major? Maybe. Okay. So at some point you get to take Math 108 or Math 219, right? Or maybe you'll be like, oh, I really want to take that philosophy class, that symbolic logic class. That's one of my favorite philosophy classes to recommend to math majors because they're like, oh, I don't want to actually take a real philosophy class. And I'll say, oh, well, how about you take one that's really masquerading as a math class? And they're like, this sounds great. And I'm like, okay, great, take logic. And then they can take a philosophy class without actually wondering about what is good or beautiful or whatever, right? Useless things. Instead, they can do logic, which is useful. No. Do I have any philosophy majors in the room? Yeah. So are you triggered right now? Mm, yeah. Did you guys like a what can you do with a philosophy major? Yeah. Would you like fries with that? Right. Um, yeah, and speaking of which, I guess, I mean, somebody didn't get a Whopper, right? And Adam's not here. So what happened? Somebody buy that man a hamburger. And how does the jingle go? Ketchup, mustard, but whatever, pickle. Yeah. So okay. All right. So this sort of is how the secret sauce, if you will, of how you figure out how to put the circuit together in the first place, right? Now, when we started this, I just gave you a diagram and said, do it. And then we figured out what it did later. If we think through logically, we could figure out what it's going to do before we even put it together. Okay. All right. So the next circuit that I'll have you guys build, okay, is let me go back to the pi. What about if we flipped the situation here? So in this circuit, the one that you guys wired, our NAND gate, I have P's in parallel and N's in series. What about if I put the P's in series and the N's in parallel? Okay, I could do that. And this is what it would look like, right? Suspiciously similar looking. It's almost like I've just flipped the thing upside down, except who's still at the top? The P's, and who's still at the bottom? The N's. Okay, so I haven't truly flipped it upside down. All right, so let's reason through this, right? Under what circumstances will there be a connection from plus 5 volts to the output? Well, let's think about the P side, okay? When can current get from plus 5 volts through both of the P's? What has to be true about both of their inputs? They're both off, right? Because an input being, if input A is off, what does that do to the transistor? It keeps it on. The P types, remember, are backwards of what you think. Okay, so when can we go from 5 volts straight to the output? What has to be true about both input A and input B? They both have to be off. Okay, so let's draw up a truth table like we did last time. And I swear, if there's these tiny, nubs of, does anybody see like a decently sized piece of chalk somewhere? Okay, excellent. That's not like, yeah, this is much better. Okay. Um, all right, so let me draw the truth table. So we've got A, and we've got B. Okay. Now, both could either be on or off, and there's, as we've seen, 4 possible patterns under which that could happen. We? Okay. So, what did we just say? If both A and B are off, what's going on the P side of this circuit? Is there a connection between plus 5 volts and the output? Yes. Okay. So what should I put in the 0, 0 box there? A 1. Okay. Now, we're not finished though, because we also have to make sure that the output is not connected to ground. Because if it is, then we have a connection from plus 5 volts straight to ground, and that is called a short circuit, and that's bad. Okay. 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 Shouldn't short circuits. That's bad. I don't know. How's my Mr. Mackey impression? Is it okay? Yeah. Um, I'm not very good at doing a Cartman, but oh well. Kyle. Yeah. Yeah. Or what was it? I think of this every time I go to Sparks and they're serving, whatever food, but they've also got like the impossible meat or the plant-based chicken or whatever. And there's an episode where they make fun of that. And, I just wanted to have, decent food. And, the girls, it's like, I thought you guys wanted stuff from like the farmer's market and crap. And instead they're getting like these plant-based meats. And he keeps having heart attacks. And, you know, because it's South Park, it's got to be over the top. But all right, so the inside of the circuit, we need to make sure that the inside does not have a connection between the output and ground. Otherwise, we've got a short circuit. Okay, so right now we're thinking input A and input B are both off. If input A is off, what happens here? It does not go through. It's off. What about the other one? Same thing. So is there a connection between ground and the output? No, there's not. That's a good thing because we already said there's a connection from 5 volts to output, right? So output should be connected only to one thing at a time, either to 5 volts or to ground, but never both simultaneously. Is that okay? All right, so are we convinced that we have a 1 here? See? Ooh, we. Okay, d'accord. Da. Uh, well, I would say we might all be saying da, but and who knows? I mean, but the situation in Ukraine is deteriorating by the minute. Um, so anyway, okay. So we've got 3 other cases to consider, right? Let's take when A is 1 and B is 0. All right. If A is 1, what happens to this transistor? Not going to go through, which means can anything get from 5 volts to the output? No. Okay, it's blocked. All right. On this side, can we get from output to ground? Yes, because if A is on, then what's true about this transistor? It's open, and so is there a connection from ground to the output? Yes. Okay, so what would that be? That would read as logical 0. And A and B, you see how they're kind of complementary? Like if you flip A and you flip B, does the same thing happen? Yeah, so this is also a 0 for exactly the same reason. Good? Okay. Now what about the final entry? If they're both on, then what's true down here? Do we have connections from output to ground? Yeah, we happen to have two of them, but that's okay. Still connected. What about up here? If these two are both on, what's true about these two transistors? They're both off, so there's no connection from 5 volts to output, and therefore this is a 0. Okay, so this is called a NOR gate because it's a not OR gate. Why? Because you see all those zeros? All right, well, let me draw the truth table for an OR gate, which how to circuit build it is another question. All right, the OR gate, his truth table is like so. Okay, and let me see if I can get a little bit more light on the chalkboards here. There, that's better. Good? Okay, so let's look at the OR truth table for a moment. Okay, because what does it mean in English if A or B? If A or B is true, then the output is true, okay, or 1. What about if both A or B is true? Is the output true? Yeah. For the regular meaning of OR, okay, or maybe better put, the computer science meaning of OR, which is, are both possibilities okay? Yes. So this is not the dessert OR. Okay? This is inclusive OR. We? We. Okay. So, and if I asked you, are you in math or computer science class this semester? Well, first off, what would you all say? True. Every last one of you, because you're sitting here. Okay. But some of you happen also to be in a math class this semester, but the statement is still true, right? Okay. Okay. So look at the truth table for the OR gate, and then look at the truth table for the NOR gate. What do you notice? Yeah, it's inverted in some sense, right? All the zeros became ones, and all the ones became zeros. Well, what's that code for in logic? Throwing the word not in front. Okay. And so what does NOR stand for? Not or. We have or, we have not or. Okay, does that make sense? Okay, so I will have you guys build one of these also, not right this instant, okay? But structurally, doesn't it look suspiciously similar to the NAND gates? Just with a few tweaks, but it's a very similar idea, okay? And the truth table that you should see is that its output is on only when both input lights are off, and the output is off otherwise. Okay, so it's a little different than the NAND gate. Um, okay, so this sort of begs the question, if we can build a NOR gate, and there's the circuit, how do we build an OR gate? Okay, there's an easy answer and there's a harder answer. What's the easy answer, Teo? Throw an inverter after it. Yeah, exactly. Right? So what was the very first CMOS circuit we built on Monday? We built an inverter, right? How many transistors did it take to do that? 2, 1P and 1N, right? So I could take the output of this and make it the input for an inverter, and then use the output from the inverter to drive my light. Okay, does that make sense? Yeah. So I can put these pieces together in order to make other circuits or other logic gates. Okay. Okay, and so I'll have you guys do that. Now, where we're going with this is eventually you've got 3 big breadboards in your kits, right? You're going to put a NAND gate on one of them, an OR gate on another, and an AND gate on the third. And make sure individually that all three work. Okay. Yeah, and if you need some more parts, just let me know. I've got buku to extra. Okay. Um, then what? Well, then I'll tell you how to put them together in a clever way to make a more gloriously complicated circuit that does exclusive OR. Okay, so what's the difference between inclusive OR and exclusive OR? Right. Yeah, so XOR would be what happens if A and B are both true and you do A XOR B? You get false. Okay, so this is the cheesy analogy with dessert, right? If you ask your mom for both cherry and apple pie, what's she going to do? She's going to backhand you and you get neither of the pies, right? Because when she asked if you want apple or cherry, what was the underlying assumption in that statement? That both was not an option, child. Okay. Now, I don't know. My mom, I'm an adult now, so I'm sure my mom wouldn't actually do that to me. But can we run with the joke that my mom is like a dessert Nazi or something? And so, no dessert for you. Um, yeah. Okay. So does the idea make sense? Okay. So at this point, then, did anybody have any bugs with their circuits? We get the AND gate or NAND, excuse me, gates working. Okay. Which groups have bugs? You two? Anybody else? Does it work or not? Okay. Let me see it. Plug it in. Oh, you need to upload the program to the Arduino. Okay, so do that, and then I'm not seeing anything going on over there. Yeah, you probably just need, yes, you need to upload the other program to it. So, yeah, okay. Well, do that and yeah. All right. So, sorry, there was one other thing I was going to mention. What was it? Hmm. The paper. Do I have everybody on the paper? It's made it around somewhere. Even, of course, uh, did you put yes, the douchebags who didn't make it to class today? Okay. Questions? Oh, you have a problem. Okay. So I think this is probably a good place to quit. If your thing works, bucket on the thing and off you go. And if it doesn't work, stick around and I'll come take a peek. All right. I'll see you guys on Friday.